Oh, thank you, and thanks for the invitation to speak today too. Okay, so let me say what the problem that we'll be looking at today. So the K disjoint paths problem. So it takes as input G, S, T. So G here is just going to be any graph. S is a set of vertices, say S1 up to Sk. So again, that's what this parameter K is here. And T as well is a set of K vertices. Okay, so I have this input, I have two sets of K vertices, and what I'm trying to do is find disjoint paths in the graph. So a solution is, let's say, paths P1 up to Pk. They're pairwise vertex disjoint, and now each of these paths, Pi, is supposed to link up the corresponding pair of vertices. So it's supposed to link Si to the vertex Ti. So a solution is paths P1 to Pk so that they're pairwise disjoint. And Pi links Si to Ti for all I equals 1 to k. So, no, I'm not assuming that S and T are disjoint, but I am assuming that all these K vertices are distinct.
You mean pairwise disjoint, you mean vertex disjoint?
Yeah. So you can now start playing with different variants of the problem, right? Whether you want the paths to be pairwise vertex disjoint, pairwise edge disjoint, etc. Today we're only going to care about pairwise vertex disjoint.
The graph can have multiple edges, or this is just a simple...
So since I'm caring about pairwise vertex disjoint paths, multiple edges aren't going to change anything. And, you know, really what is coming into play here is the order of these vertices, right? Menger's theorem tells me that if I just take any two sets of K vertices, I can either find K paths between them or a small cut which separates them, right? So what really makes the problem interesting here is the fact that I'm ordering the vertices of S and T, and I want to link Si specifically to Ti with its corresponding path. So in reality, G can be either directed or not. So in the undirected case, well, I'll just say this is the KDPP, K disjoint paths problem. And in the directed case, I'll say the KDDPP, just so I can get through the day writing everything on the board. And now, when I'm looking at directed graphs, I obviously want these paths P1 to Pk to be directed paths. So it's a path that starts in Si and follows the directed edges all the way to gets to Ti. So I'm primarily interested today in this directed case, but we're going to talk also about the undirected case as a way to sort of give us hints on how to go forward tackling the directed case. Okay. So in the undirected case, it's a theorem of Robertson and Seymour that for all K, there exists an O under the third time algorithm to resolve, well, okay, so let me say, to either find a solution to a given K disjoint paths problem, GST, or determine that it is infeasible. Right. So n here is just the number of vertices in G, and this, I should note, was later improved to n squared by Kobayashi, and Reed. But it's important to note that the problem requires k to be fixed here. So in reality, if you look at the running time of this algorithm, there's a function f of k hiding in the front here, which is super exponential.
Is the best n squared, not n log n or something?
Yeah, well, that's debatable. I mean,
Okay.
so n log n is also, there's a conference paper announcing it, but it's a long ways from being actually written up. So what about in the directed case? So it's a theorem of Fortune, Hopcroft, and Wiley. That the problem is NP complete even when k is equal to 2 to determine feasibility of the k-directed disjoint path problem. So let alone even finding a solution, just the decision problem of determining feasibility is NP complete for k equals 2. And now Thomasson, after this, conjectured that, well, let's do something to try and make this problem more tractable. And so Thomasson proposed that we look at highly connected instances of the graph. And in doing so, perhaps the problem would become feasible. So this was like in 1980 that he conjectured this. So that there exists an f of k such that the k-directed disjoint paths problem is, in fact, he conjectured that it was always feasible for instances, where's my eraser? Always feasible for instances GST where G is f of k connected. So now when I'm talking about connectivity in directed graphs, I'm talking about strong connectivity. So deleting at most these many vertices leaves the graph still strongly connected for any subset of vertices. So this was his conjecture. He later proved it was false. Let me say, so why would this even possibly be true? Well, this is exactly what happens in the undirected case. So when I'm looking at undirected graphs, there is such a function f of k. In fact, the best known is 10k, where if you're 10k connected, then any k disjoint paths problem becomes feasible.
That's your theorem, right?
Yeah, that's my theorem. But it was already known for some function f of k since a long time, and there were various improvements. But that's not what I want to talk about. So what about in this? Well, Thomasson proved that it was false. So Thomasson proved that, I think, in like 92, so about 10 years afterwards. So it's NP complete to determine whether a k-directed disjoint paths problem GST is feasible even when k is equal to 2 and G is arbitrarily highly connected. So what do I mean? G is arbitrarily highly connected. You give me any bound on the connectivity, and I can find a series of instances where it's going to be NP complete, where every graph in that series satisfies that connectivity bound to solve the two disjoint paths problem. Okay, so that kind of kills it. How can we get around this? So the way I propose that we get around this is by looking at the half-integral k disjoint paths problem. So the half-integral disjoint paths problem, so say the 1/2 k dd pp, you take as an input the same instance that we had before. So gst, an instance of the disjoint paths problem, and a solution now are paths P1 up to Pk again, such that every vertex is in at most two distinct PIs. So they're not pairwise disjoint now, they're allowed to overlap at a vertex, but at most two of them are allowed to overlap on any given vertex. And again, the usual thing, PI links SI to TI. And now the theorem is that for this problem, the analog of Thomasson's conjecture does hold. So theorem. And now this is joint work with my graduate student Irina Muzzi and Katie Edwards and myself. So that is, there exists a function let me write it over here, actually, sorry. Since there exists a function f of k such that for every let's say every instance of the half integral k directed disjoint paths problem, GST, such that G is f of k connected, is feasible. So as long as I'm sufficiently highly connected, then I'm guaranteed that there is a solution. And in fact, there exists an O of n to the constant time algorithm to find the solution. Moreover, as opposed to what we were saying before, for the Robertson-Seymour algorithm for the k disjoint paths problem, there's no hidden function f of k. That is, this is genuinely polynomial even for k part of the input.
So in polytime you can find optimum k or?
No. Because the graph has to be highly connected. So I can't solve it because I can't do a binary search, because at a certain point the graph won't be sufficiently highly connected to go higher.
How bad is the function?
Pretty bad. It's like tower of height like k squared or something.
So the algorithm either find the linkage or discuss it?
No. So I start with a graph which is highly connected, and then inside that I'm using like Menger's theorem for that connectivity a whole lot of times. But But I assume the graph is that connected to begin with. Yeah, I guess the theorem would go through, or you'd find a connectivity, a cut set violating the connectivity. Yeah. Okay, so how does the proof work? What's the proof idea? And now I want to go back and look at what happens in the undirected case for a bit of a clue on how we should tackle the directed case. So observation, which is that in the undirected, KDPP. So if G is 2K connected and G contains a, say, K, 2K subgraph, so a click on 2K vertices is a subgraph, then any K disjoint paths problem is going to be feasible. For all choices of S and T. Disjoint. All right, so what does that picture look like? Here are my two sets of vertices, S and T. And I assume the graph has a click subgraph K here, right? So just by Menger's theorem and the connectivity, I can find disjoint paths from S into the click and disjoint paths from T into the click.
2K.
Yeah, so I need 2K, right? Because I need K paths from S and K paths from T. And now at this point, huh?
K is a capital.
That K, that's a capital K. Yeah. So no matter how these paths come in by Menger's theorem, the click allows me to link up the appropriate endpoints and get the linkage that I want. So that's great. Unfortunately, requiring the graph to have a big click subgraph is too strong a condition. So it's a theorem of Robertson and Seymour, which is that if G is 2K connected again, and G contains a K, 3K minor, then the same condition, the same outcome holds. And again, any G, so any K DPP G ST is feasible. So what is a K 3K minor, in case you haven't seen that before? So K 3K minor is disjoint, pairwise disjoint subsets of vertices x1 up to x 3k such that, so I want 5 of them, etc. So what I want to happen, I want that G restricted to xi is connected, and for all I and j, there exists an xi to xj edge. So it's sort of a generalization of containing a click subgraph. Here, I'm looking at sort of clumps of vertices, sets of vertices here, with the requirement that I want them all to induce connected subgraphs. And I want between every pair of them, some pair of those vertices are adjacent.
Connectivity, doesn't that imply a large click minor anyway?
Yes. So I'll get to that in just a sec. So let me see, first off, how we use it. And specifically, why I had to bump up from 2K for the size of the click subgraph to 3K here for the click minor. Because since these are subsets, here I have a lot more than just 2K vertices. I don't know a priori how many vertices I have. So when I follow Menger's theorem and link from S and T into the set of all these xi's, I make it lucky. And the paths may land on separate vertices, but it might not happen. It's possible that some of those paths will land in the same bag. So the point is that I bump up the size of my click here to 3K, and then I'm able to extend these paths inside the click. So that now I have to throw away this bag, but then on the remaining bags, the paths all land on distinct xi's. And once those paths all land on distinct xi's, I just use the fact that they're all connected and pairwise connected by edges to connect up the endpoints as I want. Okay, so now coming back to your question, yes, the whole point was that there is no function f of k which forces a k 2k subgraph in a graph. Whereas the nice thing about working with a minor here is that if the graph is sufficiently connected, I can force a click minor using just connectivity. So the corollary here is that by making the graph sufficiently connected, I'm able to solve any k disjoint paths problem. Okay, so that was in the undirected case. Yes?
What happens if these two yellow passes share a vertex in some component?
Yeah, so this was a pretty hand-wavy version of the theorem. So in fact, you need to sort of, it's not as clean as this. It's not that you just link in and try to extend the paths. You have to do sort of a clever induction proof to make it go through. But the rough idea of what's happening is this. Yeah, I can show you the proof afterwards if you'd like to see. It's not hard, but it's sort of technical induction hypothesis that makes it go through. Okay, so this was the undirected case. Now what happens when I'm looking at digraphs? So first observation is, well, question, observation, what do we want to use for a click minor in a digraph? And I don't have a good answer for that one. We're going to even put that one aside and go to an even more fundamental problem. Is that this proof technique is never going to work to resolve the integral disjoint paths problem. So why is that? Well, here's my set S, here's my set T, and assume for the moment that I have a good definition of directed click minor. So I can sort of link back and forth in either direction from these bags, I don't know. But just what happens in the basic application of Menger's theorem. Menger's theorem can give me k paths from S directed into this set of vertices. It can give me k paths coming back from the vertices to T, but I can't simultaneously do those things with Menger. Menger is only monodirectional. It gives me paths going from one set of X to another set Y. But doesn't give me paths both from X to Y and Y back to X simultaneously. But if we lower our sights a little bit and are looking just for half integral paths, we don't care that the linkage from S to here intersects the linkage from here back to T. Right? Because these yellow guys are all pairwise disjoint. Red's pairwise disjoint, so any intersection out here is going to be still respect half integrality. Okay. So it won't work for the integral k disjoint paths problem, but so far we're still alive in terms of working for the half integral problem. And now, what about the click? The click minor. In fact, since we're only looking for a half integral solution, we're going to use something that's sort of analogous to a half integral click minor. So in fact, it's called I have to decide. Yeah, okay. Let me see. So define depth to bramble of size L is subgraphs B1 up to BL of a digraph G such that BI is strongly connected. They pairwise intersect. And every vertex is in at most 2 BIs. So size is just the number of the BIs that I have. They're all strongly connected and they pairwise intersect. And the depth here just means that every vertex is in at most 2 of them. So the proof outline has 2 steps. One is, how do we force a depth to bramble? With connectivity. And 2 is, how do we use a depth to bramble to link up a la Robertson-Seymour?
Explain quickly the issue that happened here. Why didn't that happen in the undirected case?
Because in the undirected case, I could take all my paths at once, right? I could just take 2k paths starting here, and there was no worry about going backwards on a path.
Okay.
So if you, in a sense, if you change the problem and say you want to find the direct sort of path that goes one direction and change one direction backwards, then you can sort of disjoint Wollan as well, or going forward and then at some
Yeah, I see what you're saying. And then so your path is allowed to switch direction exactly once or something like this?
At most once. Then you maybe have to sort of disjoint Wollan.
Yeah, but I don't think you can force an integral click minor, a directed click minor, with just strong connectivity. And there are technicalities under here that are going to make directly putting the analogous proof through. So I don't know. That's a good question. I don't know though if that's not feasible or not. Okay, so for the rest of the talk, I'd like to just sort of give an outline of how these two steps proceed and then conclude with just giving some open problems of what's still happening. So the first step here is, how do we force a depth 2 bramble? Okay. So define a well-linked set X has the property that, so for all x1, x2 contained in X of the same size, there exist that many paths. So let's say size of x1 equals size of x2 equals some k. There exists k directed paths from x1 to x2, and let me say in G minus internally disjoint from X. Right? So if I have my whole set here, X like this, and I pick x1, x2 of the same size, then I can always find disjoint paths of size of x1 going to x2. So, I mean, note that if G is L connected, then any set of size less than or equal to L is strongly connected. Is well linked. But I'm going to prove it in a slightly more general context because we do so for other applications. So the starting point to find the bramble is a very long path so a directed path P, so that on P I can find subpaths P1, P2, dot up to say P L squared. So that on each of these guys I can actually think of this as two smaller subpaths. Called P1 in, P1 out, etc. So that on each of these guys, it contains a set xi in or xi out such that the union of all the xi's is well linked. Again, so let's say, take a step back here and look at, so my starting point for finding the bramble. I want a very, very long directed path so that I get a well-linked set sort of spaced out over the course of the path. So I break it up into little chunks called P1 in, P1 out, P2 in, P2 out, etc.
You just cut some point?
Yeah, I'm just gonna greedily find this and use that as my starting point. So now, using the fact that I'm well linked implies that there exists a linkage, say Qij from xi out to xj in for each pair I and j. So at this point, if you've read Diestel's proof of the grid theorem, it's sort of starting to look familiar for how Diestel goes about constructing a grid in the grid theorem. I fixed this linkage going like this, right? And now,
So that's for any ij?
and I do this, I do this for all I and j. And now look at two of these linkages. So xi out, xj in. So I'm switching up my picture here. X I prime out, x j prime in. So if this is q I j, this will be q I prime j prime. Right? So I have these two linkages, qij and qi prime j prime. And now just sort of an immediate Ramsey argument says that either I can find many of the red linkage which are pairwise disjoint from many of the blue linkage, or I can find many here which pairwise intersect many of the blue. And those are sort of two separate cases we have to deal with. So what happens if I get a large number of intersections? So many qij intersect many qi prime j prime. So I get a very large pairwise intersecting here. So again, if you have in the back of your head Diestel's proof of the grid theorem, that's where he goes about and finds a grid. Sort of the system of paths which pairwise intersect a big system of paths here, and eventually if you clean that up, you're able to find a grid living inside that common intersection. But we're looking for a bramble, but we're looking for a bramble in the directed graph sense. So the sets of the bramble, the sort of certificate of big directed tree width, these have to be strongly connected. This graph that I've drawn so far could in fact be acyclic. All these guys go down, all these guys go left to right, and the whole thing is acyclic. So I'm not going to be able to find a bramble of strongly connected things which all contain cycles, right? So how do I get around that? So I look at my linkage here and remember that, so just focus our attention on blue for the second. And remember that this is in a well-linked set. So I also have paths coming back this way. X j prime out to x I prime in. Out. Sorry. I can get this yellow linkage going back the other direction. So blue is a linkage, yellow is a linkage, but now how do the yellow intersect with the blue? And they can do all sorts of wild intersections. So you need a lemma, which says that
The assumption is the union of all inset and outset is welling.
yeah, so the union of the whole big union. So that was the union of all xi in, the union of all xi out. That whole thing together is all well linked. Okay, so these yellows are all looping back this way, and the lemma says that either we get a big depth to bramble in yellow plus blue, or the following happens. So I can find this. So I can find little sections of 3 blues and 2 yellows, 3 blues and 2 yellows, so that the yellows here are disjoint from the blues here. Right? So I have the yellow paths going back. In general, there was no control over how yellow intersected with blue, but if I don't find the depth to bramble we're looking for, I'm able to find little chunks where the yellows here are disjoint from the blues here. So each of these is, for whatever reason, is going to be 3 blues and 2 yellows, but I can get as many of those as I want by starting off with these 2 guys being sufficiently big. And then we're done. Because now what happens? So I need all my colors. If I take one of these guys, one of the yellow, blue ones, and then I applied the same theorem to get yellow, red guys, right? I know all red and blue pairwise intersect. That was the case I was in here, where many of the reds intersected many of the blues. And now I take one of these blue, yellow paths, and then at the two endpoints, it has to intersect a red here, so I follow back also a red, yellow, red. And in the end, I have a strongly connected graph here, right? Moreover, if I take two of these guys, right, they're going to be pairwise intersecting because each of these ones contains a whole red path and a whole yellow path. And every red path intersects every blue, each one contains a whole red path and a whole blue path. And since each one contains a whole red path and a whole blue path, they're going to be pairwise intersecting. Okay? So that's how I'm finding my depth 2 bramble. In the case where they have pairwise many intersections. So I applied this, again, what was our original setup? We had this huge long path P here, and I had broken it up into many pieces. Right. And now I apply this lemma between every pair, and I'm able to reduce down to the case where I'm going to get a genuine red linkage. All these guys are going to be pairwise disjoint. And in fact, I have almost like a directed click here, right? Except the red are pairwise disjoint. These subpaths here are pairwise disjoint, but I have no control over how red here intersects with white. So I still am only going to be able to find a half integral click minor, and I have to be a little bit careful in how I pick it. But given that the whole thing is comprised of sort of a red linkage and a white linkage, I'm able to find the depth 2 bramble that we're looking for. Okay, so that is how we find a depth 2 bramble using just connectivity. And so let me preemptively answer one question. You may be saying to yourself, didn't Korebashi and Kreutzer just prove the directed grid theorem? Couldn't you extract a depth 2 bramble from their grid theorem? And the answer is yes. I mean, given the grid theorem, you immediately get a depth 2 bramble as well. But we want this runtime on the algorithm to be genuinely polynomial, even when k is part of the input. So I'm not able to use any of their bounded tree width arguments because they're all going to have super exponential factors when I allow k to be part of the input there. So I sort of have to do everything manually by hand here. Okay. Any questions before I go on to step 2?
Maybe could you explain the last case, what you're doing?
Yeah. So at a certain point a long time ago, I wrote L squared here.
Yes.
And so you think of this as an L by L grid. And now what are your bags going to be? You take rows and columns.
Right.
There's one bag, and then here your next one is going to be this guy, and then coming down like this. So those are pairwise intersecting, and each white path is in at most 1, and the red paths are in at most 1, so you're able to get it you're able to maintain this half integral property. You're able to maintain the depth 2 of the bramble in this way. Okay. Okay, so using a depth 2 bramble. So this is the second step there. So let me say, to duplicate a vertex, is just what it should be. So I take 2 copies of the vertex with all the edges coming in and all the edges going out. And I connect them by an edge in each direction. Right? So I really am just taking, doubling each vertex. Okay, so given the depth 2 bramble, if we double each vertex in BI intersect BJ, row I and J. So if I double each vertex, which is shared by 2 of these sets, BI, right? In the end, I'm left with genuinely pairwise vertex disjoint, strongly connected subgraphs. In the resulting graph, we get, let's call the resulting graph G prime. We get pairwise vertex disjoint, strongly connected subgraphs B1 up to BL primes. Right? So identify each of those guys to a single vertex. Collapse it down to a vertex. So after I do that, the resulting contracted vertices form a bidirectional click subgraph. And I try to link S to the resulting click and link from K back to T. So now, if I can find those paths, right? If I can find those paths, well, that's exactly what I wanted in the original graph, right? I wanted an integral linkage from S into distinct bags of now this depth 2 bramble, and then another linkage from distinct bags of this depth 2 bramble back to T. And maybe one thing that's setting off alarm bells, right, is that we want to make sure that we're half integral. We doubled a bunch of vertices. How do I know that I didn't double some vertices and now in the original graph the linkage, say from S to the click, is no longer an integral linkage? Well, remember, we only doubled the vertices that were in the BIs. So in this graph, where I did that and then collapsed each of the BI primes to a single vertex, every vertex outside K is a genuine vertex of the original graph. Right? So I don't have to worry about that problem. But what I do have to worry about is that now maybe these guys don't exist. Right? Specifically, I could have a separation of order less than K separating S from my bidirectional click K, right? How could that be? Well, it better be the case that it's not a cut in the original graph, so there have to be contracted vertices here in the cut set. And I'm not going to draw the edges, but remember, those form part of the click there. So specifically, all the K vertices, because this is a bidirectional click, they all have to live on this side of the separation. Okay, so what do I do? Uncontract the K vertices. K is now two separate things. The click vertices in the cut set. Right? I can just reopen those back up and think of those as their original strongly connected graphs. And eliminate any unnecessary duplicates. So remember, again, maybe I had to duplicate some vertices to get these guys to be disjoint. If I don't need those guys anymore, I just re-identify the duplicated vertices and go back to a single vertex. Right? And now I threw away at most K bags in my bramble, but I still have a very big bramble left to work with. Moreover, this particular separation is no longer a K separation. Right? Because all of these guys all got blown up into a big set of vertices. Right? So that particular K separation is no longer an obstruction for linking S into the remaining blue vertices. Okay, but maybe there's another one. So I find another separation separating, but then again, it has maybe a couple of bags that I have to worry about. I blow those up, and I keep going. Right? So I do this 2K times. I keep finding a separation of order less than K, separating S from the blue click. And anytime I do so, I blow up the blue vertices in that intersection, in that cut set, preventing it from being a cut in the remaining graph. So do this 2K times. And I claim that after I do that 2K times, S is no longer separated by a small cut from blue, from the blue click. And why is that? Well, assume it was, right? So again, here's my set S. Here's my blue click, and assume that I again had a less than K cut separating. So it has some blue vertices in the cut set and some original vertices here. Right? Okay, so look at the original vertices here. There's at most k of those. So of my set of 2k separations that I found along the way, there has to be one of those separations where the blown up bags, where these blown up guys avoid these vertices. So look at that separation. It is also a separation separating blue from S. But now where are these yellow blown up guys? The yellow blown up guys, well, they can't be here in the intersection of both those cut sets because I picked them disjoint from white. And they have to be connected to the blue click. So they all have to live over here, distinctly on that side. And I have then, at most, original vertices of the real graph here. But now look at this cut here. That's a vertex cut in the original graph separating S from everything blue. And every vertex in that cut set is a real vertex of the graph. Moreover, it has size at most 2k. So if I pick my strong connectivity to be 2k in the original graph, I just got a contradiction. Almost. There's a fair number of technicalities that I'm hiding here, right? So one is, how do I know that this separation is non-trivial? Maybe the only things here are S, and it's all contained here. In which case, it's not a contradiction to connectivity. Okay, so I have to pick more separations with higher connectivity to avoid that problem. Another issue is that I've only done things one directional, starting at S. At the end, I also remember I have to get back from T going the other way. So that's also going to add technicalities, and I have to bump up my connectivity for this. So this is a fairly high-level idea, but this is essentially what we're doing. We're working in this graph where we duplicate to get our bramble to be a general integral click, and then we keep finding separations, violating it until we're able to actually get a separation violating connectivity in the original graph. So in case you care about what the original bounds are, where'd they go? One, two, three, 4, 7, 8. Here we go. So theorem.
You mean FLK or?
Yeah, I mean what you actually care. So for all k, there exists a t such that if g is 36 k to the third plus 2k connected, and there exists a bramble of size t and depth 2, then any instance of GST, any instance GST of the k, the half integral k directed disjoint paths problem is feasible. And we can find the solution in time O of k to the fourth n squared. Okay, so we saw the two steps. We saw that by having a huge amount of connectivity, we were able to get a depth 2 bramble. And then we saw how, with a much more modest amount of connectivity, we're able to use the depth 2 bramble to link up half integrally any choice of k start vertices and k terminals. So let me just say, so that shows that the problem is always polynomial time solvable for hugely connected graphs. What about lower bounds? So the problem is still NP complete. Even when, for instances, GST, where G is epsilon k connected for all epsilon less than 1. So it's NP complete even for highly connected instances where highly connected here is epsilon k. I can get arbitrarily close to k connected. And now one open question is what's happening here? Is there some sort of sharp bound on the connectivity where the problem jumps from being NP complete to polynomial time solvable? And my guess is probably no. I bet that would be unreasonable. I bet there's probably some point where it stops being, where it's not actually NP complete, but is still, polynomial time solvable for fixed k, and then at a certain point it jumps again to being genuinely polynomial time solvable for all k. But it would be interesting to have a better understanding of what's happening in this jump between when it's NP hard to when it's genuinely polynomial time solvable. And then I think a more interesting open question is, do we really need this bound on connectivity? How do you resolve half integral k directed disjoint paths problem in general? So specifically, does there exist an algorithm in time O of n to the f of k for some function f of k?
Wait, on the left-hand side you said it's NP complete, or is that? Wait.
With k as part of the input.
Oh, this is for fixed k.
Yeah, so and this is for fixed k. And in fact, even the case k equals 3 is open. And I worked reasonably hard on k equals 3 and wasn't able to solve it. So even k equals 3 I think is a distinctly non-trivial problem. And I'll finish there.
Right.
I just realized my watch stopped, so I have no idea how long I've been talking. But
Right.
okay.